Thank you. Well, good afternoon, everybody. My name is Luis Palacios. I am going to present you part of the work we have done along with Florian Moharit in our lab in the CA in France. And well, the topic, the main focus of these works are the integration and acquisition of knowledge in model-based systems engineering. Next slide, please. So let's just go through it. So first, I'm in the LSEA lab, so it's embedded and autonomous systems lab. So that's who I am, who we are. Please come back. And well, basically, our interests go into managing the knowledge into the organization, knowledge in the engineering process, which is more specific to this workshop and these topics. We're interested in different viewpoints and perspectives and abstraction levels that can happen and arise in engineering processes and management of knowledge in general. We are interested into knowledge acquisition, integration, and reuse. And we are also interested in smart assistance, knowledge management, and semantic interoperability. So those are the umbrella topics of the lab in this regard. Next slide, please. So currently, where the problematic that we are tackling is that we have sophisticated tools for model-based systems engineering. And they support explicit meta languages like UML or XML v2. Yet there is limitations in the semantics. How could it detect semantic errors? How can it integrate maybe expert knowledge, or how it could formalize the knowledge from some of the users? If the user is doing some activities in the tool, we would like to capture part of this knowledge, or most, or capture the knowledge in order to also reuse it, transfer it, and assess it. So we are addressing these limitations by annotating the UML models with domain-specific ontologies. So it's related to some things that we have seen in the sense that we have a language that refers to a specific domain. And then we assume that under this language, most of the concepts and the relations and the vocabulary you will need are already present. And we can use it to provide it to the system engineer to annotate his model, and then this model can be will carry part of the semantics of the ontology, and therefore we would have a UML model or a model in terms of the ontology of the system that has been designed. Next slide, please. So these annotated models, that means the models, the UML models that have been annotated via our approach with the vocabulary of the ontology, they are suitable for reasoning tasks. We can do consistency checking, instance checking, and some of the reasoning tasks that you might know or have heard about. And most importantly, and we are targeting, is that if we have captured knowledge through this process, and this knowledge can be reused and shared. Can be reused, for example, if we have developed a system to impose a new subsystem into a further iteration for someone else, or for example, we have learned how to develop a task or how to make some specific designs. It can be shared with other semantic compatible tools, so that either automation or other tools or other actors and stakeholders can interact with it. So specifically, we have targeted Papyrus and UML. Papyrus is a tool that is very related to our lab, and that it's used for model-based systems engineering, and UML is its default language. We have targeted the autonomous systems domain because we are also interested in standardized languages and specializations of these standardized languages, which is part of what our argument is about, that the language should be consensuated. And we, under the autonomous systems domain, we have targeted the UAV's application domain. So that's our context. Next slide, please. So this is an overview of how we do it. First, we have a union ontology. This union ontology means that we have an application domain, for example, the UAVs, integrated into some standard. So in this way, the standards are too general to be used, but in this case, we have a standardized domain-specific language. Then we select the concepts and relations that are required, and we integrate them and make them available into the model-based systems engineering tool. And then we have the user in the loop, in the sense that it's the user who is going to use the tool, which and then out of his knowledge and out of his expertise and out of the things he's doing in the tool, we are going to extract back to the ontology, in terms of the ontology, part of what the engineer has taught. So that's why we are talking about extracting or knowledge acquisition in this part, and the reuse, because we can go back in the loop. So this is please next slide, yes. So this is an overview. I'm not going to go through the details, but what you should see is that this is a system design of a drone system, which is on the first box on the left. And the three boxes on the right means that it has a battery, it has a motor, and it has a propeller. So these are generic types that come from the ontology, which is the background language. And then these are instantiations or are subclasses of it. And on the right, you have also instances of these classes. So one of the difficulties that we have found when trying to extract, let's say, information from a model-based systems engineering tool into OWL is that it's not clear what is a class, what is an instance. There can be an overlap because of points of view and because of different interpretations. So on the top left and on the top right, you see definitions 7 and 8. What we are doing is what exactly, there's a set of mappings, and these mappings applied to the UML model gives you TUML on the left, and a set of mappings applied to the model on the right gives you AUML. This stands for T box and the A box of the system. Next slide, please. And then the T box, if you see in the example 5, looks like a T box, and it talks about concepts and relations, but talks not at all about individuals. So it's the rules that govern the world, so to say, and this can be applied to generic things. And on the bottom, the part that is related to the instances has been translated into assertions in the A box. So in this, using this approach, we have tried to formalize how to specify these transformations and to unambiguously define what exactly means, what is the specification of the system, in this case a T box, and what is the instance of a system. Because the specification could be shared or improved to define new systems and to impose constraints on further models. And the instances can be improved and generated as well, or evaluated against other systems, or to be proposals. If there is an instance, it could be thousands of instances that could be valid, and then we can explore models that respect the language of ontology. Next slide, please. And these two, basically, this is the other two last definitions that we have introduced. In the left, you see TUML, which is the T box or the system specification. And it says union O, which is the original ontology, should evaluate to true. That means that if you consider the O on the left, the background knowledge, your system has to be consistent with your background knowledge, with your vocabulary, which is evident, but it here is established, logically established. And on the right, we say that also the AUML, which is the farthest thing on the right in the box, which is the system instance, has also to be consistent with the system specification, and both of them have to be consistent with the original ontology, which is the background knowledge. In this case, the language that we select at the beginning serves as background knowledge and as theories of how the world should work, and we should comply to them. Next slide, please. So basically, the contributions of our work are the integration of standard and application domain ontologies, so integration of specific application languages into standardized languages. Second, we have a methodology and a proof of concept of the integration of these languages into model-based systems engineering tools. Then we have the extractions, in quotes, from these toolings back into the terms of the ontology, so we can run reasoners and make other operations on top of it. And we have the last parts of our work have been the formalization of the approach in order to determine and precisely define each one of the elements that are involved into the whole life cycle. So that's our work. Thanks for your time. And if you're interested, our contacts are in the slides.